Hi, welcome back to Yeti. Today we're going to start building up our Fourier expertise. We're going to have a whole bunch of lectures on Fourier. We're going to start by motivating these lectures with this super cool application, shark tracking. And we're going to try to answer a question for shark biologists, which is, how fast is the shark that we're currently being studied? In this picture, you see a bunch of Harvey Mudd people and some CSU Long Beach people. They're attaching this smart tag onto a leopard shark. And what's going to happen is that leopard shark is going to be released in that tag, which has a camera, it's got an acoustic pinger, and it's got accelerometers and gyroscope set. Those are going to collect data for us. We're going to recover that tag later, and using that information, we're going to again answer the question, how fast is the shark? Let's just watch the shark. As it swims around with this super cool intelligent tag, we call it a smart tag, you can see that the shark's head goes back and forth. And we're going to use that back and forth motion to try to estimate the forward velocity. Now, as you can imagine, the faster the shark swims forward, the greater the rate that that shark head will move back and forth. Let's get motion sick. Here's what the shark sees. So like I said, on that smart tag, there's a video camera, and you can sort of see what the shark sees. Let's zoom ahead, see if there's anything more exciting. Ooh, I see bubbles. There is a boat. It's making some pretty sharp turns, but you can see it goes back and forth. And like I said, you watch this long enough, you will get motion sick. But there's something that we can look at here, the frequency of that head going back and forth. And you can see in this equation, it's related to v, the forward velocity of the shark. This is some work done back in 1989. The idea here then, if we can figure out the frequency of the shark's head going back and forth using this smart tag and the gyroscopes on board, you can then estimate the forward velocity. This is what that data looks like. As a function of time, the shark's head, its heading angle, goes back and forth. And you can see there's definitely some periodic motion going on there. That's what we're trying to find, f, the frequency of the shark's head going back and forth. But how are we going to extract it from this particular data set? We're going to start by using a Fourier series to do this. So here's our question. How do we decompose that time domain signal into a frequency domain representation? So instead of it varying as a function of time, we want to see that same data vary as a function of frequency. To do this, we're going to start with a very simple function called x of t. And we're going to start by saying, you know what, we can approximate this function, or any function in general. It doesn't just have to be the shark's heading as a function of time. But let's just pretend it's any general signal, x of t, and we're going to approximate it with what we call building block functions. And that approximate function might be the red dashed line here. We'll call x hat of t. Now, x hat of t, we're going to say, is a infinite sum. In this case, it's infinite. Later, it might not be infinite. But in this case, it's an infinite sum of scaled basis functions. C sub k is the scaling coefficient, and then we have this basis function. So again, we're going to estimate our original function x of t with x hat of t, which is an infinite sum of scaled basis functions. Now, we haven't said what the scales should be, and we haven't said what the basis function should be. I'm going to propose one basis function. All right, seems pretty simple. May not be the best, may be the best, we're not sure yet. But let's just get us going with this really simple example where the basis function in this case has a value of 0 most of the time, but has a value of 1 between the value of t equals 0 to t equals capital T sub s. All right, so you can see it pictorially, you can see it as a function. We're then going to use this as a basis function to approximate signals. We can also use it in a time-delayed case. Going back, you see the same function can be time-delayed here by that value of t sub s, and now we have the same thing, only it's shifted in time. In fact, we could have a whole bunch of these shifted in time. If we sum them up and scale them, maybe a good way to approximate that original function x of t with a whole bunch of scaled p of t's. And you can see that some of them are higher to sort of approximate this part of x of t, and some of them are lower to approximate this part of x of t. And you can get a whole bunch of these shifted versions of p of t that act as your basis functions. Mathematically, this infinite sum of scaled basis functions might look something like this, where the basis functions are those p of t's, or shifted versions of them, and we scale them with the actual height of x of t at the starting of p of t. You can see that we're scaling them right when p of t starts in all cases. That's just one way to do it. I'm not saying it's the best yet. And once you remove some of the additional red lines, you can see that this red dashed x hat of t does a reasonable job of approximating x of t. I just sort of drew that out for you to sort of get an idea of how you might start to think about using a whole bunch of building block basis functions to approximate some general x of t function. So here's a question. If we're given the set of basis functions, for example p of t, how do we pick the coefficient values, the scaling values c of k? In the last case I showed one example where we just take the leading edge of p of t and see what is the height of x of t at that point, but maybe we can do something better. Our strategy is going to be to minimize what we call the integrated squared error, which basically says we're going to take the difference between the original function and our approximate function, square it, and integrate that over all time. So how would we find the coefficients that minimize this? Well, from calculus, we can take the function we want to minimize, take the derivative of it with respect to the variable we're minimizing over, and equate it to 0. Pretty common calculus method. Let's see how that works in an example problem. We're given this function, x of t, which looks like it grows with time between 0 and 1 seconds. We're going to use that same basis function, and we're going to use the period of that basis function to be 1 second. And for that case, we're going to minimize the squared error to find the scaling coefficient. So what does that look like pictorially? The function we're trying to approximate, x of t, actually looks something like a sawtooth. Between 0 and 1, you can see it equals t, so it's growing with time till it gets to 1, and then it goes back to 0. The basis function, p of t, like we showed last time, just has a value of 1 between 0 and the period. In the period in this case, t sub s equals 1. So this is our building block function that we're going to use to approximate x of t. And we're going to try to use the minimization of squared errors to find c0, the scaling coefficient that will go with this basis function. Now when we do this math, it's going to be good to note that, as said before, our approximate function, x hat of t, is going to be the sum of all of our scales times our basis functions. And in this case, we really only need one scaled basis function, k equals 0. Because our basis function only has non-zero values between 0 and 1, the same time span that our actual signal that we're trying to approximate is non-zero. So we really only need to say, hey, for this basis function, how high should it be? How much should we scale it to best approximate this sawtooth? Let's go do the math. We start with this minimization from calculus, where we want to minimize our integrated squared error with respect to that coefficient that we're trying to solve for and equate it to 0. Let's plug that in. This is the sawtooth. This is going to be our scaled basis function. From calculus, we know that we're going to take the derivative of that, bring the 2 down, and then we're going to take the derivative of this part of the ISE because it's the only part that contains C0. Pull that out. We've got a negative here because of the negative sign that was here. And so now we have to take this derivative. Taking that derivative with respect to C0 is just going to leave us with our basis function. We also substituted in here C0 times that basis function. And now let's take those and split them up, multiply, or distribute, I should say, our basis function to both terms in brackets. And let's do one more thing. We're going to break this out into 2 different integrals. So we just took these 2 terms and put the integral over both of them. Now one thing you might have noticed is that back up here in the original ISE, it was from time negative infinity to infinity. I actually put time 0 to ts because that's the only time that the functions are not 0. Now using this and equating it to 0, we can isolate the one variable we're looking for, c0, and write it out. Let's continue this and we'll copy this function to the next page and we'll start subbing in. The original function we're trying to approximate is t between 0 and ts. The building block function has a value of 1 between 0 and ts, and we substitute that into the bottom as well. We can integrate both the top and bottom numerator denominator and get these values. 0.5 times ts squared over ts. If you recall, ts is equal to 1, so we can get a value after all this number crunching to be 1/2. What were we calculating again? We were calculating the scaling coefficient that says how much should we scale our basis function by to get the best approximation of the original function. Here's that original function. We'll scale p of t, our basis function, and it says scale it by 1/2. So instead of it being the original value of 1, it becomes 1/2. And you know what? This actually does a pretty good job of approximating this sawtooth, given a pretty rudimentary basis function. Let's summarize what we just did today. One, we talked about approximating signals with building block functions that we're going to call basis functions. We talked about the approximation being a sum of these basis functions, but they're scaled by coefficients that we're going to call c of k in our notation. I still have left a bunch of open questions, and the two main ones being, what is the best way to pick those scaling functions? And we actually also haven't decided what is the best way to pick our basis functions. We're going to pick up these questions as we go through this series of lectures, but hopefully you've taken away this idea that we can take a general, time-varying continuous function and approximate it with a infinite sum of scaled basis functions. Thanks, and see you next time.